Hello. I'm assuming that you have gone through the example 1, the ideal Brayton cycle problem, and we're going to build up on that by solving an actual turbine problem, actual Brayton cycle problems, example 2, by leveraging the solution we already have for the Brayton cycle, ideal Brayton cycle. So to do so, we go to the test code for the ideal Brayton cycle, copy that, and come to a new window, and we launch the same app, PG model. In the I/O panel, we paste the code, click there and paste the code, and the load button. In the cycle panel, you can see that the efficiency is 50.96%, which is what we were expecting. If you notice, the 50.87% was the answer in the first problem. Okay, so now how do we change this solution to suit our new problem? In the new problem, in the actual cycle, what we got is the isentropic efficiencies for the compressor and turbine are supplied to be 90%. So I've already drawn the TS diagram. As you can see, the blue cycle is the original ideal cycle. And we introduced a new state at the compressor exit, 2 for the ideal exit, 3 for actual. Similarly, at the end of turbine, we have introduced a new state 6. So the 1, 3, 4, 6 is my new cycle, and I have already solution for 1, 2, 3, 4, the original blue cycle. So we'll need the compressor efficiency and turbine efficiency to find these two new states. I've already written the equation that we need. The compressor efficiency is basically the amount of work you need for an ideal divided by for an actual compressor. In the turbine, it's the opposite. The lower number goes on top, so it will be actual 4 minus 6 divided by the ideal 4 minus 5. So based on that, we get enthalpy expression for state 3 and 6, our missing links for the actual cycle. Now that we have the formulas to find the new states, we go back to our solution of the ideal cycle, go to the I/O panel, isolate all the parameters we already supplied, and add to that our new parameters, namely the compressor and turbine efficiencies, which we are defining new variables, eta C and eta T, as 0.9. Of course, we can change their values later. As we click the calculate button, these values are registered. We come back to the state panel now. And notice that state 1 and 2 doesn't need any alteration, as we already know. To insert a new state, we click here, that introduces state 3 and shifts all the other states to the right. And for pressure 3, we'll probably write equals P2 is an easier way to write. And mass flow rate is already equal, and it's not isentropic, so we initialize entropy and write the formula for H3, which you already wrote down in the PowerPoint slide. H1 plus H2 minus H1 divided by eta C. Now, if you didn't declare eta C, this would be white, will have a white background, but if it registers, it will become green background. And we found state 3. In the graphic panel, state 3 should be slightly to the right of state 2. 3 has been renamed 4, and we need to now create a state. So let's go and check state 4 for sure. Anyway, we'll call it P4 equals P3. That's an easier way to write. So there we have it. All the states have been now computed. So if we go to the graphics panel, we should see state 6 to the right of state 5. We come back to the device panel, and let's go over all the devices, making sure the inlet and exit states are correct. As you can see, device 1 was set up for the ideal compressor 1 to 2. So we better correct that to 1 to 3, the actual compressor exit. Q dot equals 0, so we calculate the new value of the compressor power. For state 2 and 3, for other devices, I've already corrected the inlet and exit state. For device 2, the heat exchanger will be 3 to 4, calculate, and for the turbine it will be 4 to 6, and finally for the second heat exchanger it will be 6 to 1. Now that all the devices have been done, analyzed, in the cycle panel we will have the cycle complete message, and you can see the thermal efficiency has been found, W.net has been found, and it's important to always compare W.net with Q.net to make sure they are equal, the solution is consistent. If you go to the I/O panel, isolate our variables, we can change these numbers and quickly make parametric studies. Suppose we say the turbine is perfect and the compressor is perfect. Well, what does it mean? That means if I calculate these, we should get back our ideal. Do a super calculate? The answer should be same as the ideal cycle efficiency. Recall that this was exactly what the ideal cycle 50.87, and for the current problem we got 39.96. So we can go back and reproduce our simpler solution, or we can isolate and do different sort of study, like what will compressor efficiency, how will it affect the turbine performance, or the turbine efficiency, how will it affect the overall gas turbine cycle performance. So I'll leave it here, and again we are going to build upon that in the next example, launching the solution from where we left off.